Is this sentence familiar to you? And sometimes it sounds like the perfect solution, right? Hello, I'm Clara Pina Coronado, and this is Solid State Foundations, a series on solid forms, polymorphism, and crystallization science. In this video, I want you to understand that even though it sounds like the perfect solution, amorphous material is not always the safest option. Amorphous means the molecules are not arranged in a long-range order crystal lattice. In simple terms, they are disordered. Because of this high energy state, amorphous materials often show higher apparent solubility and faster dissolution rate than the crystalline material. But here's the deeper layer. That same high energy state makes them thermodynamically unstable, and sometimes with enough time or stress they tend to crystallize. Maybe you're asking yourselves, why does this matter? It matters because stability drives everything: shelf-life, manufacturing, and regulatory confidence. Amorphous systems are very sensitive to both temperature and humidity. A key concept here is the glass transition temperature. The TG is the temperature at which an amorphous material transitions from a rigid, glassy state into a more mobile, rubbery state. Below TG, molecular motion is highly restricted. The system is kinetically frozen, which helps maintain physical stability. Above the TG, however, molecular mobility increases significantly. This increased mobility allows molecules to reorganize into a lower energy crystalline structure, meaning the risk of recrystallization rises sharply. Humidity adds another layer. Water can act as a plasticizer, lowering the TG of the system. This means that even if your product is stored below its normal TG, absorbed moisture can effectively bring it closer to the glass transition, accelerating instability. In other words, you gain solubility, but you assume physical stability risk. If not properly controlled, your bioavailability advantage can literally disappear over time. As you can see, it should never be a desperate last-minute fix. The key questions are: do you understand the TG? Can you control the molecular mobility? Will you stabilize it with a polymer matrix, for example, an amorphous solid dispersion? Identify the risk, test it under stress, and design a control strategy from day one. And if you can't, in Solitek, we are here to support you with solid state characterization, glass transition analysis, and stability studies. Also, we design fit-for-purpose preclinical gas formulation when amorphous is the right path. Because, do not get me wrong, amorphous is not unsafe by definition, but it is never risk-free. So next time you encounter a brick that's molecule and someone suggests going amorphous, you'll know to ask, do we truly understand how to control it? I hope you have enjoyed this new section of Solid State Foundations. If you like this episode, let us know in the comments and follow us to stay ahead of solid state chemistry. See you next month!